So good morning, students. Last class we were discussing about the machine independent assembler features, and in that we just seen this program blocks as well as control sections. Program blocks are the logical partition of the program within the source file, same source file, and these concepts will be useful further in our linkers and loaders. So that's why I'm stressing on this particular thing. So wherein the control sections will be of ultimate use to show you the concepts of linking process during the loading of the program. So for that reason, yeah, program blocks are created by an assembler directive use, and wherever the use comes, the location counter will be initialized and it will be grouped together during pass, first pass of your assembler. Your assembler collects all the instructions belonging to each program blocks and gives the consecutive addresses, and the consecutive addresses are given for the subsequent program blocks also. So this is done by pass one of the assembler, and after that it will behave as a normal program, and your pass two assembler does the expansion of your mnemonics to opcode as well as operands to its addresses, and assigns the memory if at all it is a declarative statements. Fine. Okay, and a symbol table entry will also be made. Yeah, we have seen the control sections. Control sections are actually the physical partition of the program. The same source program might be written in multiple source files. Such sort of thing we call it as control sections. And here we don't use an assembler directive, as we are writing the source code itself in multiple what we call source files. So that will going to physically partition your source file. Going further, we use two assembler directives, the external def extdef and extref, so as to specify that the symbols which is declared in the current control section may be used by the other control sections is called as extdef, and extref specifies the variables or constants which are declared in some other control section but is used in this control section. Please remember, these variables or constants which comes under the category of extdef and extref must be a direct addressing. It cannot be relative addressing. This should be remembered. This is direct addressing. The reason is the complete address should be modified during the process of program linkage. So for that reason, we don't go for format 3 instruction, but instead we go for format 4 instructions. Yeah, the control sections, here we have 3 control sections. The default control sections, or the main we can call it as, which is having 3 symbols in extdef, that is buffend as well as length, which is defined in this control section but used in other control section. extref, we have 2 variables under that, read record, write record, which are referred in this control section but are declared in some other control section. So this will going to be the default control section, and you can see that return address, buff and buffend are being declared either as a declarations or as using the symbol defining statements in the current control section, right? And even the length is being declared in the current control section. But the read record control section is using buffend and length, and the read record itself, which is we can think of as a subroutine, which is written in another file itself, is being referred in the default control section, and in the write record is also referred in current control section. These two are the 2 subroutines which does some reading the record or writing the record. So that's particular thing. And you can see there in the default control section we have 2 instruction plus jsub read record, which is a format 4 instruction, and similarly we have plus jsub write record, which is also a format 4 instruction, which is invoking the subroutine read record and write record. Means to say we are switching our control to that particular control section, which is written in a separate source file. And similarly, in read record control section, we are telling load to T register the buffer end and store to the accumulator buffer comma X. The buffer end and buffer both are not defined in the read record, but is defined in the main control section or default control section. In the similar fashion, we have write record, which is using a length as well as a buffer, which are also being defined in the default control section, but is being used in the write record control section. So these resolution of the external references will not be the part of your assembler, but the assembler should make a mechanism so that it can convey these specifications to the loaders or linkers. Certain times loaders will have the linkers together, certain times the loaders will not have the linkers, but the linker will going to be an independent part. We shall discuss that in our module 2. Fine. This specification is done by assembler by specifying a modification record. Or each external references will have one modification record which specifies which is the starting address to be modified and how many half bytes from there should be modified. That will be usually 5 half bytes. That means 5 bytes. Means 5 into 4 will going to be equal to 20. So, and which address should be added during the load address? Each control section may get its own address. So that address, starting address, should be added to the modification of that particular variable's address. So this is the specification done by your assembler. One means to say your assembler leaves blank the operand address, which and all are external references. All the external references, operand address will going to be made as blank, and the same entry will going to be written into your object code file. So during the linking and during the loading, after getting your load address by the operating system, based on the load address, that particular absolute address will be added to those text records whose operands are 0. So this is how the external references are handled by your assembler. So we are looking only from the part of assembler. So we shall see the other way of it also when we discuss about the linkers, how these things are resolved by your linkers, when it is absolute addressing, when it is relative addressing, all these particular things we shall discuss in the loaders and linkers. Right. Yeah. Yesterday, and in the previous class, we also went ahead and seen the assembler design options. We can implement the assemblers not only using 2 passes, but the other variations can also be done. That is one pass assembler, wherein the entire assembling, that is pass 1 and pass 2, is completed. Definition and expansion both are completed in a single pass. Yeah, yes, this can be done, but provided we have all the declarations before the instructions. Means we have all the symbol defining statements before the instructions. If this is done, we can go for a one pass of the assembler. So there are 2 variations of one pass assembler. One is called as load and go assemblers, means which the source program will be there in the memory. We don't have the source program will reside in memory. So it acts something like as an interpreter, wherein after one pass a complete object code is generated and immediately the code will going to be executed. Means to say the no updation will happen to the contents that is present in your secondary storages. This can be used when we go for what? Memory programming. Means to say we don't have a storage, we just have the memory, and the assembler should reside there and should do the conversion during that time. And here also all the symbols need to be defined early, but though even the symbols are defined early, the forward jumps may be there. Something like at the 003 we have a label loop, and the label loop appears at 0036, then the address of loop will only be available once we assemble the instruction at 0036. So as to handle these sort of forward references, we can leave that particular thing blank, and we're going to be made entry into the symbol table as a blank address, and when the address is gone, we'll update that particular address into the symbol table. So this way we can go for a load and go assemblers. We complete the assembling process, converting the mnemonics to operand during pass 1 itself. but only the forward references are kept blank, which will be filled as soon as we get the symbol's address. So that sort of one pass assembler design, we call it as load and go assemblers. Okay, I think we have discussed all these things. The second variant of the one pass assembler is write the object code file. Means the earlier load and go didn't load the object code file, but directly assembled and put that loaded it for the execution. But the write object code file as a second option or a second variant of the one pass assembler, wherein similar to our two pass assembler, the object code will be generated just in one pass. Here also we need to have all the symbol defining statements should be defined early. Second thing, it generates the object code and writes it into an object code file. Again, the same problem appears here. How shall we handle the forward references? The forward references are handled by writing the text record of your object code with blank address or the blank operand address for all the forward references. And when we get the operand address, that particular text records will be modified. So no need to use any modification records here. Just we're going to replace the operand address when it is got in the text records only, right? So this sort of implementation, we call it as write object code file. Okay. And anyway, though this write object code file is a one pass assembler, it goes one more pass for only those symbols which is having forward references, because once a symbol is got, we should go to that place of text record and modify it, right? Just like a reallocation of the program, how it happens, the similar fashion here also, without using the modification record, we will be changing the addresses when it is called. Right. This is one of the design option. Means we have the normal design of the assemblers using two pass. That's what we learned. We learned the algorithm also and everything. So the variant design options, what we have is we can go for a one pass assembler, wherein we can do the entire thing in one pass, but the declaration should be written early. So then that's all. Yeah, right. But we have a problem with our symbol defining statements, that is specifically our EQU statement. The EQU can define a symbol. Left hand side we're going to have the name of the symbol, which is user specific. On the right hand side we can have a constant, we can have variable, we can have a location counter address, that means a star when we use. We can have a location counter address, or else we can have an expression, right? We can have an expression. So after evaluating the expression, we may get an absolute value or a relative value. That will be the value assigned to the symbol that is used in your EQ, right? This we have seen already, right? Something like I have written 0 EQU 50. And 0 is a value, 0 is a user-defined symbol whose current value is 50. I can also write it as 0 EQU A plus B, wherein A is this variable already declared or may not be declared. B is a variable which is already declared or may not be declared. If suppose variable A and B are declared before, then you have got the address of A and B, and that could be used to compute the value of 0. If not, if A and B not been declared earlier, then the 0 cannot be evaluated. 0's value cannot be evaluated. The symbol 0 value cannot be evaluated until we get the value of A and B. If that is present later, then we should wait until we get the address of A and B. Getting the point? We shall see with the example. I'm just setting up a preamble. So this case, the pass 2 assembler will also fail and pass 1 assembler will also fail. Why? Pass 2 assembler will going to do all the declarations after all the instructions. Fine. Each symbols will be assigned address in pass 1. But A and B, if at all is declared, 0 EQU A and B, if at all is declared after 0 being defined, then the 0 need to wait till the addresses of A and B are defined. Similarly, if it is a one pass assembler, it will also fail. Obviously, though we have the symbol defining statements early, the A and B value, if at all it is declared later, means after 0, then it needs more than one pass. So for that sort of situations, we go for what? Multi-pass assembler. Multi-pass assemblers need multiple passes on the source code, so that not for your instructions. I am making you clear, not for your instructions, because converting the instruction to opcode, converting the opcode means converting the operand address to the memory, are the two tasks that we are supposed to do. So in the typical assembler, we did it first one in first pass and the conversion in the second pass. That's simple. But because of these expressions, the operand address will not be available in the first pass itself. So we may need to take multiple passes before going for a conversion. Such sort of situation is handled by the multi-pass assemblers. And I am telling you, this and all are because of the symbol defining. So if at all your program is not using symbol defining statement, yes, fine, you can go for some typical two pass assemblers for assembling in definition in one pass and conversion in the other pass. Or you can use one pass assembler itself if you are able to make the declarations before the instructions. Fine. But the multi-pass assembler is needed in the case of what do you call the symbol defining statement. Have a look at this. Now we have multi-pass assemblers. Have a look at this example. That is going to make us the understanding. A is a symbol. We are telling A EQU B. We don't know what is B. B is written later. B EQU C. We don't know C. C is declared later. Declarations. These first two are symbol defining statements. The last one is a declaration. C, reserve word 1. We are assigning address for C, which is an integer variable. Now, C will going to get the address in password, but A will not get, B will not get, because B is dependent on C, A is dependent on B, means A is transitively dependent on C. So, A cannot be evaluated until B is got, or B cannot be evaluated until C is got. So, we need multiple passes. This leads to a transitive dependency. So, we need to have multi-pass assemblers. So as to handle such sort of situation, we'll use we're going to store these symbols into symbol tables, and we'll evaluate. And after the evaluation, we're going to put the absolute or relative address, absolute value or relative address also after the values. So as to handle this sort of situation, your symbol table is equipped with this sort of fields. What fields? First one is label. Anything that is appearing on your left hand side, user defined names, we're going to call it as a labels. The next field we have is def var, number of variables on RHS not yet to be defined. For example, in the case of A, B not yet been defined. So that comes into the category of your def var. For example, for your B, C is yet to be defined. So C comes into the category of def var. Getting the point? Fine. Expression or value. For example, for C, this is a word 1. Whatever the your pass 1 of your assembler gives the address, that is going to be the address for your C. So that is going to be your value for C. But what is the value for B? B is dependent on C. The expression for B will going to be your C. What is the expression for your A? B is the expression for your A. So until you get the value of B, you cannot evaluate A. As simple as that. Dependent label, name of the label which this label is referring. The name of the label which this label is referring. For B, A is the referring. For C, B is the one who is referring it. For C, no one is referring, because C is just a declaration. So for C, who is referring it? B is referring it. B, who is referring it? A is referring it. Like this. We shall see a much better example, and we're going to understand this concept. So this is a mechanism or the fields what we use in our symbol table for handling the dependency created due to the symbol defining statements. in a multipass assembler. It's not multipass assembler is a what we call additional feature. This is uh, due to the requirement that we need to handle the dependency created due to the multiple a symbol defining statements using expressions. Fine. Okay. See the example. I have numB, which is a symbol, user defined symbol, equal to maxlen by 2. Maxlen divided by 2. We don't know the value of maxlen yet. Maxlen equal to buffer end minus buffer. We don't know the value of buffer end and buffer. PREVB, that's one symbol that user has defined, which is equal to buffer minus 1. And later, buffer is having its own declaration. Buffer reserve by 1000. We are reserving 1000 bytes for buffer, which is at the address. The address 1030 is given by your pass one of the assembly. And then buffer end equal to star is been defined. And it is again a symbol definition. I mean, we have only one declaration here, that is buffer. Rest all is a symbol defining statement. Buffer end equal to star, which is given address by your what you call pass one as 2030. Now, though we have got the address of buffer and buffer end, and even buffer end is referring to the current location counter value. That is because of the star. Maxlen, buffer end, buffer minus 1, this is all as supposed to be evaluated. So we cannot do it in a single pass. We need multiple passes. So that's what we mean by this. Yeah, in pass one, what happens to our structure entirely? So numB is a user defined symbol, that is the label. It is dependent on one more variable. That's why in depth where we have written as #1 means it has got one dependency. What is the dependency? What is the expression? Maxlen divided by 2. Whom on it is depending? It is depending on maxlen. And nobody is dependent on numB. So that's why dependent label is marked as black. Depth label is marked as dash because no one is dependent on numB, but numB is dependent on maxlen. So that's what is the thing. Next label is maxlen. Maxlen is having two dependencies. That's why #2 is written there, which is buffer end minus buffer, right? And who is dependent on maxlen? numB is dependent on maxlen, right? Because so as to evaluate numB, we need maxlen divided by 2. That should be done. So I'm going a bit slow so that you can understand the relative relationships of these things. Okay, the next label is PREVB. PREVB is having one dependency because it need to get buffer minus 1. The expression is buffer minus 1. So expression / value, why is it written? As the passes go on, as we get the value of means addresses of the dependent variables, means dependency variables, we're going to replace the expression by the value what we are getting. That value may be either relative or absolute. We are not at all bothered about it. As we get the values, we're going to update this particular table, right? And nobody is dependent on PREVB. That's the reason depth label is marked as black. Buff, yes, it is no dependency because it's a only declaration statement, and its address in pass one only we're going to get, that is 1030. Yeah, who and all are dependent on buff. Maxlen is dependent on buff, as well as PREVB is dependent on buff. So we are having two dependencies on buff, right? And buff end equal to star, and on buff end we don't have any dependency, right? Means for evaluating buff end, I don't want anything else. So it got the address directly 2030. The address of buff is 1030 plus 1000 will going to give you 2030. And who is dependent on buff end? Yes, we have maxlen, which is dependent on buff end, because maxlen can be evaluated by using buff end minus buff, right? Please understand this example. They won't ask you to solve a problem, but you should have a specific example to explain. Not only here, this sort of examples we will be using again in our linkers. Okay, so this understanding will make your understanding easy in the case of our linkers and floaters, right? So that's why I'm stressing much on it, right? So this dependency itself can explain how the linker works in a particular situation, right? And the linker comes into existence because of this. Okay, maxlen Yeah, buffer end is on buffer end. We have the dependency of max len because max len expression is buffer end minus 1. I think hope you understood this particular table. So this is showing the dependency. Only two symbols got evaluated now. That is your buff, which is a declarative statement, which got the address 1030, and the buff end, which is a symbol defining statement. Though it is symbol defining statement, it got its address because 1000 bytes are reserved for buff. The next location counter value is 2030. So that is the address of your buff end. Fine. This much is done in pass 1. So two symbols got evaluated. Three symbols are still remaining in your after pass 1, which is not yet evaluated. Okay. We shall go further. The same thing. We are in pass 2 now, second pass. In pass 1, I got the address for buff. I got the address for buff. After pass 2, who and all can be evaluated. So as I got the address for buff, PREVB can be evaluated. Am I correct? PREVB can be evaluated because I have already got the address for buff, which is 1030 minus 1. That should be the address for your PREVB. You can see that PREVB is evaluated, got the address 1029 because buff minus 1. Buff already has got the address 1030. 1030 minus 1, 1029 is the address of your PREVB. So we got the value. So the expression is removed. If you can see in the previous slide, we had the expression. In the previous slide for PREVB, we had the expression and there was no dependency on PREVB. The same continues here also. PREVB don't have any dependency, but PREVB now got the address. And max len got the address buff end minus buff because buff end has also got the address, that is 2030. Buff also has got the address 1030. 2030 minus 1030, I got the value 1000. This is completed, means this got the address. That's the reason earlier slide we had the expression buff end minus buff, which got converted into a value now after pass 2. But still one more is remaining. Who is that? Max len, because I cannot evaluate numB until max len got evaluated. Max len got evaluated in the second pass. PREVB got evaluated in the second pass. But we need to go one more pass for evaluating numB because it's a transitive dependency. numB depends on max len depends on buff and buff end. So for that reason, numB should wait until the max len gets evaluated. So we go next. This is the last pass, wherein max len divided by 2. So numB got the value 800 because your max len value is 1000 hexa. 1000 hexa. Remember, all addresses will be in hexa. 1000 hexa divided by 2. You got 800 hexa. Fine. Now you can see the dependent labels are all blank and require all of them are 0. So we took just for defining the symbol addresses 3 pass. So we may need one more pass, or we should need one more pass for means expansion of your mnemonics to opcodes and operands to its addresses. So this is how the multi-pass assembler functions. That's the idea. So means for defining the transitive dependency of the symbol defining statements, wherein those symbols are defined or declared later than the symbol defining statements, leads to the transitive evaluation of expressions. For that reason, we need multi-pass assemblers. Yes, fine. This completes your assemblers in all possible ways. All concepts of your one-pass assemblies, two-pass assemblers, algorithm, data structures, conversions, everything we have thoroughly gone through. Please refer to the videos so that you can get the clear understanding from starting 1 to the, this is I think is a 12th video. So each of is 30 to 35 minutes. So you can get a clear understanding of module 1. And our module 1 is not ended here. Module 1. Okay, 1 second. Mhm. Okay. Module 1 didn't end it. Module 1, we have one more concept, that is macroprocessors, which is a small one, for which this understanding. Yeah, I know this screen is not visible because I need to switch to the slide, but that didn't happen. Fine, no issues. Okay, already the timing warning also has came, but please refer to the video, you can get the understanding, right? Uh, Module 1's macroprocessor, I'll going to handle it in the next session, wherein we're going to completely handle the macroprocessors. I thought this could be finished. I felt the detailed discussion of it. This is needed. The next class, we're going to handle the macroprocessors, and then we move on to the loader something else. Fine. And the plan is that after this, the last thing that we're going to continue in the entire syllabus will be your parsers. Whatever we have left at the top-down parsers, we have completed and left. The bottom-up parsers we shall continue as a last thing, and the rest part of the compiler design, what we have, we shall complete that, and we'll come back to our what you call parsers. So we shall continue the second module, and then the fifth module, and then back to your fourth module. Fine. So we shall complete everything in a sequence. Fine. Thank you. Thank you for joining. We shall meet in the next class on Monday.